One way surfaces can decrease their high value for surface energy is to allow things to adsorb onto that surface. So we have a solid, and as we know, it could have initially a very, very high value of surface energy. So what can happen is as gas atoms collide, or if it's exposed to a liquid, molecules in the liquid phase, as they come down, you'd expect them to sort of just bounce off, but they can stick. And so over the course of a few milliseconds, we can start to coat this surface, and eventually there's an entire layer completely covered with gas atoms. And so they're not gas phase anymore. So for instance, if we did this in air, we'd have mainly oxygen and some nitrogen bound to the surface. And unless we are working in a very, very high vacuum, you should basically consider all solid surfaces to have this add layer of gas atoms that are bound to the surface by van der Waals interactions, because that can reduce the surface energy of that solid. If we assume that there's some sort of ordering in both the add layer and on the substrate, then there may or may not be a relationship between those two types of ordering. So what we call commensurate ordering is sort of like if you were building with Legos and you had a block, and then the next block that went on top of it might not be exactly the same size, but it has to be aligned. They can't be offset by 30 degrees. That's commensurate ordering. We could also have incommensurate ordering. And that's sort of like if we had a table, and you can see that the table, if it's a wood table, it's going to have some sort of wood grain to it that's aligned in a certain direction. And we would put a tablecloth on that. The tablecloth isn't restricted in terms of the fibers of the tablecloth. The tablecloth has its own fibers, but they don't have to be aligned with the fibers in the wood. We can put them at any angle we want. So there's no relationship between the add layer and the substrate, whereas with commensurate, they have to be aligned. Okay, so I notice the alignment does not have to be, there's several sets of angles that would satisfy this. We could twist these Lego bricks by 90 degrees before we put them down and they'd still fit. Okay, so we're going to spend the rest of the time talking about commensurate ordering, because if there is some sort of relationship between the add layer of adsorbed atoms and the substrate atoms, then we have to specify what that relationship is. And to do that, we're going to use Wood's notation, which basically tells us the orientation and the spacing of the add layer. In these diagrams, the substrate will be black and the add layer will be green. So if we imagine putting atoms on this, we can see we've got a square unit cell on the substrate, and we've got a square unit cell for add layer, and they're exactly the same orientation and size. So this is called a one by one add layer. By contrast, in this example, we have something that on the x-axis is the same distance, the unit cell is the same length as the underlying unit cell, but in the y-axis, the add layer has a unit cell that's twice as big. So this would be a 1 by 2 add layer. We can also have add layers that are rotated. So here we have an add layer where the unit cell is rotated by 45 degrees from the substrate unit cell. And if we look at the distance here, we can see this is an equilateral triangle, and so we can figure out the length of the cell, that hypotenuse just using the Pythagorean theorem, we've got 1 squared plus 1 squared, so we get square root of 2. So this we would write as a square root of 2 by square root of 2, because that's the length of the side of our unit cell here, and it's rotated by 45 degrees. So we look at this case, we're offset by 30 degrees from the underlying, I'll draw the unit cell in here. We can see this unit cell is offset by a 30-degree angle from the underlying unit cell. And since it's offset by 30 degrees, we can see we can construct a 30, 60, 90 triangle. So this one would be a square root of 3 by square root of 3 R30.